Okay, so you saw from the intro video that I had sort of a bluish purple solution and I added a little bit of acid and it changed pink. The question is, why? Well, the solution contains basically a pH indicator, which is a colored compound that changes color when it's either associated with a hydrogen ion or disassociated with a hydrogen ion. So in this particular case, it's blue when it kind of bluish purple when it doesn't have a hydrogen ion, but when you add acid, it gets attached to a hydrogen ion, and in that case, it turns pink. Now, litmus is a classic pH indicator. Okay, so why does it change color? Well, we're going to go over what I just said again. Okay, so litmus, again, binds to or loses hydrogen ions. When it's bound to a hydrogen ion, it is red in color. If it's present in a solution and you add some base, the hydroxide ions will react with the hydrogen ions, forming water. So this goes away, this all becomes water, and you're left with this litmus without a hydrogen attached to it, which is blue. Now, we can turn it back the other way if we just add some acid. So if we take some acid and we've got our blue litmus that doesn't have a hydrogen attached to it, but now we add extra hydrogen ions, we can drive it back to the form where it's got a hydrogen associated with it, called the protonated form, and that's red. So you have a compound that is either red or blue. It's blue without hydrogen ions attached. It's red with hydrogen ions attached. Now, most of these compounds change color at very specific pHs. That means very specific concentrations of hydrogen ions. So you already saw this chart in the textbook, and it's showing different compounds. So each of these is a compound that changes color at different pHs, and you can see the pH range over which they change color. Some of them, like a couple up here and this one, actually change color twice, depending on the pH. Now, if you pick just the right combination of these different colored compounds, apply them to a piece of paper, you can actually use that paper to measure the pH of the solution, because we know what color the different indicators are at different pHs. So here's an example. For instance, a very strong acid might actually be pH 1. A very strong base here might actually be pH 10. They give a whole range of colors. You can see neutral, which is 7, is sort of this greenish color. So these are more acidic, these are more basic, these are more neutral. Some pH papers can get very, very accurate results. If you look at the video, you can look at that. The pH indicators, as you're going to see, are also used in their liquid form in titrations, which we'll talk about in a bit. Now, a pH meter is what scientists typically use to measure directly the concentration of hydrogen ion concentrations in a solution. They have to be calibrated against pH standards. Well, guess what? Those are standard solutions that have to be made very carefully, like we talked about in the solution unit. Each standard solution has a known hydrogen ion concentration. Now, I'm not going to go into the specifics, but once you've calibrated it, you can put the probe into your solution, and based on the electrical properties of how many hydrogen ions there are, it will generate an internal voltage which can then be converted to a pH value by using the standard curve. No more detail here, but if you're interested in learning more, watch the video on how pH meters actually work. It's 1.5 minutes long and it's pretty cool. Now, what is a titration? A titration is a method of determining the concentration of another substance in a reaction. One reactant is prepared with great accuracy. That's called our standard solution. And we actually will know exactly how much volume of that is added to the other reactant. And of the other reactant, all we know is its volume. We don't know its concentration. But if we have our first reactant, say it's a base, so it's got hydroxide ions, and we know its concentration, and we know how much base we have to add to the acid to reach the point where moles of added hydroxide equal the moles of hydrogen ions that were present in the acid, at that moment, they're equal, and so we'll have an idea using basically simple stoichiometry. We can calculate what the concentration of the unknown is because we know its volume and now we know its moles. All right, so finally, in order to do a titration, there needs to be a visible color change that occurs at the moment there are stoichiometric amounts of the reactants together. That's got another name, it's called the equivalence point. The point at which the moles of the base will equal the moles of the acid. Now here's what titration equipment looks like. Okay, so you've got a ring stand with a clamp. This long glass tube with a stopcock is a burette. Down at the bottom, you've got an Erlenmeyer flask. The Erlenmeyer flask contains the analyte. Analyte is the solution that we're trying to analyze and find out what its concentration is. The burette holds the titrant. The titrant is the solution that we know its concentration, and we very carefully measure the amount of it that has to be added to the analyte to complete the reaction. The reaction comes complete right at the moment our pH indicator changes color. So if we pick a strong base like sodium hydroxide and a strong acid like hydrochloric acid, what we typically use is phenolphthalein because it's going to change from clear to pink right at the moment the number of moles of hydroxide ions equals the moles of hydrogen ions. So that figure, like I said, names all the equipment. It also shows the information that you need to collect in order to be able to do the math, to do all the quantitation that you need. Now, what you should actually do is take a pause and go to that, there's like a video that I attached. It's really an intro to how to use this ChemLab stuff, which is pretty cool, but it shows how to set up a titration using their virtual lab. So go there and play with that, watch the video. If you're really interested, you can actually try to set up your own virtual titration, pretty much just by following the example. Now, when we do a titration, the burette, that long glass tube, is filled with the titrant. Titrant is the standard solution of known concentration. Titration, titrant, that's where the thing comes from. The Erlenmeyer flask, which goes underneath the burette, okay, the Erlenmeyer flask, which goes underneath the burette, contains our unknown solution. That's called our analyte. It also contains a pH indicator, and that's going to help us determine the exact point where the moles of hydroxide equal the moles of hydrogen ions. Now, when the color change occurs, it actually has a different name than equivalence point. The color change indicates the end point of the titration. In actuality, at the end point, we will not be perfectly at the equivalence point, but we'll be really close to it. We'll just be very, very slightly beyond it. We'll have added just maybe a drop too much, but we'll be really close, so it's pretty accurate. The equivalence point has a different meaning, and that is where the moles of hydrogen ions exactly equals the moles of hydroxide ions. Okay, so here is an example titration with HCl and NaOH. Now these are the numbers that we're going to have to collect. First, we got to put our sodium hydroxide in the burette. We need to know its concentration, and we need to know the air. Now, this is not the air from the burette. This is the air in the solution, how it was made. So you can see that it's pretty well made. It's only got a 0.005 plus or minus 0.05 absolute air. So it's a pretty good solution. Right. Now, the other thing we need to know is the volume of the analyte. That's the unknown. We don't know what the concentration is. It's an unknown concentration, but we need to know exactly the volume. Now, if we use a graduated cylinder with 1 mil markings, we can estimate the volume to 1/10 of a mil plus or minus half a mil. The next thing we have to do is add some phenolphthalein to our unknown acid, to the analyte. We don't add a pH indicator, it's not going to work. Now, we don't have to use phenolphthalein, but phenolphthalein works really well for this. Now, we got to figure out how much of this known solution was added to get to the equivalence point. So we have to write down the initial volume. Now, burettes are weird at the top, as you fill it, you'll see the numbers go down. So at the top, it'll say 0. At the bottom, it'll say 50. So when you put in your solution, you write down whatever value you see. In this case, it's 24.23 mils, and it's plus or minus 0.05 because the markings are 0.1 milliliter, which means the absolute error is plus or minus 0.05 milliliters. Now, we keep adding solution until we see the phenolphthalein change pink. And when we do that in this example, it happens when we've added 32.13 milliliters. So how much did we actually add? We have to subtract. Do you notice that final minus initial will give us the correct volume? Now that's how much we actually added. Now, think about it. We know the milliliters that were added. We can convert that to liters. We know the molarity of the sodium hydroxide, 0.100 moles per liter. So if we multiply the molarity times the volume in liters, that'll tell us moles of sodium hydroxide. Now, since there's one hydroxide per compound, that'll also tell us the moles of hydroxide that we added. Now look at our analyte. Our analyte has it's hydrochloric acid. There's one hydrogen for every chlorine. So at the point where everything is reacted exactly, where all the hydroxides that we added have reacted with the hydrogen ions to make water, the moles of OH minus must equal the moles of H plus. So this calculation down here, when we use the volume of the titrant and the concentration of the titrant, which tells us the moles of hydroxide, also tells us the moles of hydrogen ions. And since there's one hydrogen ion per compound, that tells us the moles of the actual hydrochloric acid. If we have moles of hydrochloric acid and we can divide it by the volume of hydrochloric acid in liters, we'll get the molarity. And that is what we've been trying to find. So take a moment, do your calculation, and then see if this is what you come up with. All right, so calculate the concentration of cell in the flask. You should have 0.0162 with the correct sig figs. Now we're going to stop here. Tomorrow we'll pick up where we left